In the last lecture, we have seen the requirements to be met while doing windowing, how to make transition widths smaller, and how to reduce the ripples. Today we will discuss the filter specifications. Designing of an filter depends upon three crucial points. First is called gain, second called attenuation, and third is called frequency bands. Most of the times gain and attenuation will be treated in the same column, sometimes calculated in terms of gain, sometimes calculated in terms of attenuation, whereas frequency part is subdivided into two parts, that is called pass band and stop band. Please note this point that we are discussing right now for an ideal filter. When we move from ideal filter to realizable filter, then there will be another band which will be involved, that is called transition band. Gain of the filter is defined as G. So in decibels it is also given as G dB will be equal to 20 base log base 10 mod of H omega, right? Attenuation is denoted as A and it is 1 by G. So A is equal to 1 by G, that is equals to 20 base log 10 1 by mod of H omega, that is equal to minus 20 log base 10 H omega. Attenuation with a negative term, whereas gain in decibel is given with a positive term. When we realize and filter, we can sometimes give magnitude in terms of attenuation, sometimes we give magnitude in terms of gain. It depends upon the perspective how one designer want to represent that particular filter. So sometimes it is come with gain or attenuation. For pass band is defined. Pass band is defined from, in case of LPF, 0 to omega p. The stop band is defined from, in case of LPF, omega s to pi. Please note that in this lecture our discussion is for LPF, whereas the same discussion and most of the terms will remain same for band pass filter or high pass filter. Just the frequency domain which we are representing right now will be different, or the characteristic curve will be slightly shifted towards the respective frequencies when we discuss those particular filters. Otherwise everything in terms of attenuation, gain, frequency response or transition region will remain the same for all the cases, just their location will vary on the frequency domain points, because discriminated frequency will constitute a band that is called stop band, pass frequency will constitute a band that is called pass band. There are few points for the filter specifications, just like gain and pass band, we want to discuss right now. First, magnitude response of the filter is plotted between 0 to pi, as it is existent minus pi to pi, but in case of magnitude response we generally plot it from 0 to pi because of the even nature and periodicity of the magnitude response. all the equivalent information can be obtained if we plot a magnitude response from 0 to pi. Second point is the phase part. In general, phase response is not specified with the digital filters. So in most of the cases we will see there is no discussion regarding the phase in case of digital filters. In general, we have find out the basic phase of the Windows sequence in the first place, and we find out whenever there is a change of the sign, there is a shift of pi. So that we already knew. Filters are specified by magnitude response over the pass band and stop band. And these magnitude specifications leads to indication of pass band H frequency and stop band H frequency. Magnitude specifications require gain or attenuation or ripples. One can say any term, whatever they want to say. In pass band and stop band. Next we will discuss for the case of specification. First portion is absolute specifications. For that, we will draw a frequency response characteristics of the filter. So first we have plotted an ideal filter response. This is an ideal filter response with a sharp cutoff at omega c. So this is of HD omega, ideal filter response, right? This we want to achieve. What we have obtained is then realizable filter will have a response like this with the ripples in pass band and ripples in stop band. The pass band ripples will have a ripples will varying from 1 plus delta p to 1 minus of delta p with the average value of 1, which is for ideal filter. Then in a stop band it will have a magnitude or a ripple of delta s. So the frequency Wp will be this point, frequency at this point, and Ws, this omega p is the pass band H frequency, which is this, and Ws is the stop band H frequency, which is this. One can see this transition bit is due to the main lobe of the window function, and so we want to see how it is affecting in this particular case, that what will the window response of the filter. So we can see that from this point that this is the first maximum we have before the band edge, pass band edge frequency. So we'll drop a point in this window sequence, and the next maxima is at the stop band. So, and its center will be at omega c, obviously, that we have already discussed. So it will have a response like this. So if it is only a magnitude response, then it will go like this, and so on. Similarly, like this. So this is the W omega, shifted version of W omega. So one can see omega c will exactly lie at the center. That is also called delta omega m, which is equal to omega p minus omega c, also equal to omega c minus omega s. One can see Wp minus Ws is the transition bandwidth. 0 to omega p is the pass band frequency, bandwidth of the pass band. Omega s to pi is the stop band frequency, and transition band lies from omega p to omega s. Now we will see these specifications in details. First, for the pass band, magnitude is oscillating between 1 plus delta p to 1 minus of delta p, where delta p is the maximum deviation. So H omega in pass band is greater than 1 minus delta p or equal to or less than 1 plus delta p for 0 to omega p. One thing to be noted in this particular case, that delta p is much less than 1. This delta p is also called pass band ripple or tolerance. Second part is stop band. In stop band, magnitude response will oscillate between 0 to delta s, where delta s is much less than 1, also called stop band ripple or tolerance. Then the magnitude h of omega is less than or equal to delta s for omega s to pi. Here the delta s and delta p are specified as the acceptable tolerance. Thus, the specifications are called absolute specifications. After absolute specification, it is important to find out the limits. So how much we can change the values of delta S and delta P. So these kind of specifications are called relative specifications. Now we know H omega is maximum in overall response is equal to 1 plus delta P. Then to find out the relative specification, we will normalize the magnitude response, that is H omega. So if we do that, in pass band H omega will have a value from 1 minus delta P over 1 plus 1 minus delta P over 1 plus delta P to 1. In stop band, we will have H omega from 0 to delta S over 1 plus delta P. Now for better understanding and writing of the purposes, we will write delta 1 is equal to 1 minus delta P over 1 plus delta P, and delta 2 will be equal to delta S over 1 plus of delta P. Then the frequency response of the filter can be plotted as is this, where the pass band is this H omega and the stop band is this. So this is delta 2, this one is delta 1, and this point the maximum value is 1. Now if you want to find out the same relation in terms of dB, then H omega dB will be equal to 20 base log 10 1 minus delta P over 1 plus delta P. That will be equal to gain in this case, and H omega dB will be equal to 20 log base 10 1 will be equal to 0. So gain at this point will be equal to 0. Similarly, if you find out the gain of H omega in dB will be equal to 20 base log 10 delta S over 1 plus delta P. For the zeros case, it will go to minus infinity. Now this we can see this 1 plus delta P is greater than 1 minus delta P, so it is called minus AP in dB, and this is called minus AS in dB. Now if you want to plot these characteristics, we will get 0 at this point, and this is omega, this is varying, and this is H omega in dB. So we have a minus of AP here, and then we have a minus of AS, and we have a frequency omega P, and frequency omega s. So AP goes to this point, and from omega s to pi, this attenuation, it is undefined. Log is undefined. Log 0 is undefined. Okay. So 0, the maximum gain we have obtained. Then the attenuation we have seen by the ripples is of minus AP, and in stop band the attenuation is minus of AS. This is for gain. If we want to plot the similar characteristics for attenuation, then it will start from 0, and this is omega, this is pi, this one is omega s, then we have omega p, 0, omega p, minimum attenuation with the AP, and then there is a value of AS here, and at AS it will be like this, and then it will goes like to infinity. So this is the attenuation band, and this is the attenuation band in stop band. This is the attenuation band in pass band. We know that AP is equal to minus of AP is equal to log 10 1 minus delta P over 1 plus delta P. Then AP will be equal to 20 base log 10 1 plus delta P over 1 minus delta. Similarly, minus of AS is equal to 20 base log 10 delta S over 1 plus delta P. So AS will be equal to 20 base log 10 1 plus delta P over delta S. Now we want to find out the effect of delta P and delta S over AP and AS. So by using this particular relation, we can find out AP by 20 will be equal to log base 10 1 plus delta P over 1 minus delta P. So 10 to the power AP by 20 will be equal to 1 plus delta P over 1 minus delta P. So delta P can be written as 10 to the power AP by 20 minus 1 over 10 to the power AP by 20 plus 1. This we have find out for delta P in pass band. Similar approach we can apply. So it will be AS by 20 will be equal to log base 10 1 plus delta P over delta S. So it is 1 plus delta P over delta S equals to 10 to the power AS by 20. Now we know delta P is much smaller than 1. So 1 plus delta P can be approximated as 1. Then delta S will be equal to 10 to the power minus AS by 20. That is an approximate behavior. So what we have obtained in this particular case is delta P like this and delta S as this. So to design a good filter, we want minimum attenuation in pass band. So AP should be equal to 0. If AP goes to 0, delta P also goes to 0, as delta P is equal to 10 to the power AP by 20 minus 1 over 10 to the power AP by 20 plus 1. For AP is equal to 0, 10 to the power 0 will be equal to 1. 1 minus 1 will give delta P is equal to 0. So this is the first case we want. Second is for this top band, we want maximum attenuation. And we know delta S nearly equal to, we can say 10 to the power minus AS by 20. So the attenuation we want is maximum, as AS is much higher than 1, then delta S will tend towards 0, right? We can see from this particular point. So for a well designed particular filter, if we have some value of delta S or delta P, so we want those ripple to be tending towards 0 or be minimum as possible. If they are minimum, then only the attenuation will be specified accordingly in pass band and stop band. That's all for today. We'll discuss further topics in next lecture. Thank you.